So please feel free to ask questions at any time, and they are always welcome, and I don't mind being interrupted at all. I have to maybe apologize in advance because when I wrote my abstract, I said I was going to talk about both stationary and non-stationary boundary layers. But as I was preparing the material for my lectures, I realized that I wanted to cover a lot of things and always to give you a small flavor of the proofs and so on. And so I will dedicate, I guess, at least the first 2 lectures to the stationary case. I'm not sure that I will have a lot of time to talk about the non-stationary case, but I'll try to devote the last lecture to it. Although I'm not sure that I will have a lot of time. But in my defense, I think I talked about the non-stationary case in a previous Simons summer school, so maybe that will avoid me repeating myself. Okay, so I'll talk about, say, singularities and maybe instabilities. But since this will be mostly for the non-stationary case, again, I'm not sure that I will have time to cover it, in fluid boundary layers. Okay, so I will focus mostly on the 2D incompressible case. There are results in the 3D and the compressible setting as well, and I've tried to give you some references during the lectures. But let's say, okay, this is already a model case, and I prefer to focus on one setting only to give you a whole overview of what can be done. I like these models because I think that they okay, for many different reasons, but I think they are able to give an insight on, say, what mathematics can bring to modelization, say. Okay, because I think now we have a pretty good general picture of the behavior of 2D incompressible fluids within boundary layers, with both positive and negative results. And so I think that the theoretical mathematical analysis can be used to actually have a very accurate picture of when a model is valid and when it's not. Okay, so it can be used as a decision tool, say, of when a model should be discarded and forgotten about, or when it can be kept, and so on, and when it can be, say, modified or enhanced to have nicer results. So this is one of the reasons why I like this family of models. Okay, so I'll start today with a presentation of the models, and then I'll move to the stationary case, and then I'll give you a short plan for the stationary case. So first, I'll start with a general presentation and some preliminaries. Okay, so the starting point and here I'll write it in a time-dependent context, but of course if we are looking at the stationary case, then you can remove the time derivative. So the starting point is the two-dimensional incompressible Navier-Stokes system. At high Reynolds number. And so here I will denote by epsilon the inverse of the Reynolds number, so this will be a small parameter. And so if I write the equation in a non-dimensionalized way, the system reads dt u epsilon, so u epsilon is a two-dimensional vector, plus the advection term, plus the pressure term, minus the viscous dissipation equals 0. U is divergence free, and it's endowed with an initial datum. Okay, so this is really the starting point. And here, so the domain, the difficulty is the fact that the domain actually has a boundary. So the domain is two-dimensional, and so I will denote it by omega, and it's of the type I times 0 plus infinity, okay, where I will be in the following. So it can be a subinterval of R. It can be the one-dimensional torus. Or it can be, when I say subinterval of R, it can be either something bounded, the whole of R, or a half-line. Okay, these are the three typical cases. Okay, so the important thing here is that for the vertical domain, you do not consider the whole line. Okay, but you actually, so we only have a half-line, meaning that your fluid is located above a solid wall, which is at y equals 0. Okay? And so you need to enforce some boundary condition on the wall, so on y equals 0. And this boundary condition, in everything that I will talk about, is a no-slip boundary condition. Okay? So you assume that, so on the wall, you enforce a no-slip boundary condition, which means that u epsilon at y equals 0 is assumed to be 0. Okay? And so the purpose is to investigate the properties of this system as epsilon goes to 0. So on the torus, you have no boundaries, so no boundary condition. If you have a subinterval of R, then you do need to prescribe some boundary conditions. And okay, I will go into this, I hope today, at the end of today's talk. In this case, you prescribe the inflow boundary condition. Okay.
Just another question, still about the framework. So is it crucial to have y on 0 plus infinity, or can you, how easy would it be to generalize the results for example, a channel?
Ah, you mean for with two boundaries?
Exactly.
Okay, if you have two boundaries, I think it's just that you will have two boundary layers, one on the bottom and one on the top, and then you need to patch everything together. So I don't think it is crucial. I think it's just a matter of localizing things. Yes.
What about the separation between the two layers? Because I think if they are close.
No, not if they are close, but if there is a distance 1 between the two. If you have a thin channel, then you go into hydrostatic Navier-Stokes, okay, in the limit, and this I will not be talking about, but the system has similar properties to Prandtl that I will be talking about in most of the lectures. So I won't be talking about it, but yeah. But if you have a distance 1 between the two boundaries, then in that case, it's just that you have one boundary layer on top and one on the bottom. Yeah.
Short question. Is it crucial that it is a straight line? Why?
Yeah, I was expecting that. I don't think so, okay, because I think you can probably always straighten the boundary and localize things. So I don't think that qualitatively it should be very different. I'm going to talk a little bit about separation, and in that case, you know, in all the experiments that you see, quite often you look at things around the cylinder and you have separation in the vicinity of a cylinder. So in that case, you have the feeling that curvature does play a role, okay? My impression, but maybe I'm mistaken, is that it plays a role for the outer Euler flow, and that it creates, because of the curvature, it creates an outer flow that has properties to generate some separation within the boundary layer. But at the boundary layer level, I'm not that sure that curvature does play a role. And in fact, you have some transforms that straighten out the boundary and that leave the equation essentially invariant. So that's why I'm not so convinced that it does play a role. But it's a very tentative statement. I'm not absolutely positive. I can be convinced otherwise. It's just that it's a simplification. In this case, it's a simplification to assume that the boundary is flat. I will use it indeed in some cases, at least, where you use a Fourier transform or a Fourier series in the tangential variable, and in that case, it's very useful that it's actually flat. It's not always crucial. Other questions? No? Okay, so let me go on. And so the purpose is the goal is to analyze the behavior of the Navier-Stokes system with Reynolds number 1 over epsilon as epsilon goes to 0. So this is NS epsilon. Okay? And of course, if you just replace epsilon by 0, what you obtain is the 2D Euler system. So formally, when you do that, so for epsilon equal to 0, you get the 2D Euler system, which I will write, so dt ue plus ue, so this capital E should not be confused with the epsilon, right? Gradient ue, not epsilon, plus a pressure gradient equals maybe some force, but essentially 0 in all cases, and divergence of u epsilon equal to 0. The thing is that for this system, and of course on some initial data, okay, so for this system, you see there is no diffusive term, and so you cannot enforce a full Dirichlet boundary condition on the wall. Okay, so this is still in omega. So there is still a solid boundary. And so you cannot enforce a full Dirichlet boundary condition on the wall, but since the flow is divergence-free, you can still impose a boundary condition on the normal velocity. And so typically, you can assume non-penetration condition. Okay, so you assume that there is the flow remains tangential to the boundary. So on the boundary of your domain, which is just y equals 0, what you assume is that the normal component of the flow is 0, and so in this case, since the normal variable is just the vertical variable, this just means that u is equal to 0. Okay? But as you see, in general, the tangential component is non-zero. And since the tangential component is non-zero, this means that there is a mismatch between the boundary condition for the full Navier-Stokes velocity and for the Euler tangential velocity. Okay? And so in order to correct this mismatch, the proposition of Prandtl in 1904 was to, so he proposed an ansatz saying that u epsilon of t, x, and y should behave either like the solution of Euler when you are far away from the boundary, and far away from the boundary means that y is greater than the square root of epsilon. This is the typical size of your boundary layer. Okay, this can be guessed somehow because you see, so here square root of epsilon is the dimension of a length, right? You are in a, okay, non-dimensionalized length, but something like that. But when you are in a in the vicinity of square root of epsilon to the boundary, your solution should behave like a UP. Okay, so this is for my how am I? Yeah, I'm going to write it like this right there. I'm sorry because I cannot use the bold-faced letters. But okay, so I have a slight confusion of notation, but Vp of t x and square root of y over square root of epsilon. What is bothering me right now is that until now, all the U's that I used were two-dimensional. Maybe I'll put arrows to indicate that this is really a vector and it's 2D. And une télécommande. Ah oui, c'est là. And now my U's will be okay, so this is really 2D. Tac. There and there. Okay. But now this small u is just the tangential velocity. Okay. The v will be the normal velocity, and this one is the tangential one. Okay, so this removes the confusion of notation. And this is for y of order square root of epsilon. Okay, so as you can see, this is still divergence free because I scaled the normal component of the velocity accordingly. Okay, and when you plug this ansatz into the equation, what you obtain is an equation for UP, so for the tangential velocity only, which is dtup plus up dx up plus vp d capital Y up minus dyy up is equal to minus the pressure gradient of the Euler flow on the wall. Okay, so actually the pressure gradient does not vary in the boundary layer, and you still keep the divergence-free boundary condition. Okay, so this is just an equation for the tangential velocity. When you look at what happens for the normal component of this equation, what happens is just that the pressure does not vary in the boundary layer. Okay, and so since the pressure does not vary in the boundary layer, you only keep the Euler part of the pressure. And since it's the Euler part of the pressure and you are within the boundary layer, you only keep the trace of the Euler part of the pressure on the boundary, which explains why you have this quantity in the right-hand side here. Okay? So, of course, this looks a lot like the Navier-Stokes system, but there are a number of differences which I will explain right now, and I'll also talk about the boundary conditions in a moment. So the difference is that it's just a scalar equation now, okay? It's no longer really an equation for both components. You only have an equation for the tangential part of the velocity, okay? So there is just one unknown, which is UP. The VP, actually, can be retrieved from UP just by integrating the divergence-free condition. So VP of t, x, and capital Y. This is minus the integral from 0 to capital Y of dx up, dx y prime, dy prime. So I did not write it, but here y is my rescaled normal variable, so it's y over square root of epsilon. Okay, so it's not a system, it's really a scalar equation. You see that in the boundary layer, the viscous effects, at least in the normal variable, are of the same order as the convective term. This is the main input of Prandtl, that both effects would actually balance each other out within the boundary layer. Now let me talk about the boundary conditions. So on the wall, you have no slip. This is the whole purpose of the boundary layer, actually, to retrieve the no-slip boundary condition on the wall. So you have UP equal VP equals 0. And for y very large, the assumption is that the tangential velocity should match the Euler velocity. Okay, so the limit as y goes to infinity of the Prandtl velocity should match the Euler velocity on the wall, and I'm denoting this by u infinity. Okay? Okay, so this is the Prandtl system. That will be my main focus for the rest of the lectures. Yes?
Just to be sure, the fact that the pressure gradient is 0 and 1, it's up to order epsilon.
Yeah, sure, but this is the main order system. Okay, here I'm looking only at the main order. Then you can compute the higher order terms, but here my focus is really on the main order. I will talk a little bit more about what happens for the next order corrections maybe in tomorrow's lecture. Okay? Is it okay for the derivation of this system? And so.
And pressure
Hmm?
pressure is solution of.
Yeah, so the idea is that you assume that you can solve Euler, okay? You can solve 2D Euler by whatever method you want, okay? So you solve 2D Euler in this half plane, and then the solution of this 2D Euler flow will prescribe something for the boundary layer, okay? So you really solve it iteratively. First Euler, then Prandtl. Okay, because you see both the trace of the pressure and the trace of the velocity for Euler are, say, inputs for the Prandtl boundary layer. Okay, so the Prandtl boundary layer is really seen as a correction, some kind of correction to the Euler flow, but the first step is really to solve Euler. And for this system, there is no retroaction of the boundary layer on the Euler flow. They are really decoupled, not decoupled because one is the input of the other, but there is no retraction. Okay, I will talk a little bit again about some possible retroaction in tomorrow's lecture. Okay, so this system is nice because it's a closed equation. It's at least seemingly simpler than the original one because it's scalar and not vectorial anymore. The difficulty and the main source of trouble comes from this non-local transport term here. Okay, this Vp dy up. So this is the non-local transport Vp dy up. Why is it an issue? So it's nonlinear. It's non-local because you see it does not only depend on the derivatives of up at a single point, but you have to integrate over the whole segment, so it's non-local. And you also have a small loss of derivative because you do not control the x derivative a priori. Okay? In this equation, you have diffusion only in the vertical variable. So you expect to control the vertical derivatives rather well, okay, because you have a kind of diffusion-like behavior. But you don't really expect to control in a very nice way the tangential derivatives, and these are the ones that appear in the Vp. Okay, you have a kind of loss of derivative. Okay. And so, it can be argued, although it's not completely correct, that most of the problems, most of the issues in the Prandtl system actually come either from this term or from the interaction of this term with the viscous one. Okay. Okay, everything okay so far? And so then there are some questions that you can ask. And also, say, a decision tree. Okay, so the first question is the system well posed? So in mathematical terms, so what I mean by this is when you look at this system or at its stationary version, if you look at any possible initial data, does the system always have a solution? Okay, this is what well-posedness means to me. At least if you look at things locally in time and so on and so on. Okay, so this is what well-posedness, what I mean by this. And then, if it is, then you can look at, say, two sub-questions. The first sub-question is, first sub-question is, can you cook up a solution, an approximate solution of this Navier-Stokes system, okay, building on the solution that you just built? Can you build an approximate solution of the system? So again, but building on this on this solution. And then there is another sub-question, which is if you can prove that the system is well posed, so if you can prove that there exists a solution, what are the properties of the solution? And by this, what I have in mind is, does it develop any singularities? Okay? Well-posedness does not mean that the solution doesn't have singularities. It just means that the solution exists locally. Okay? But the solution that you know exists and so on might have a behavior that is not so nice, and this is something that you can also investigate.
When you talk about singularity, you talk about singularity in transfer system or in
Yeah, I'm talking about the Prandtl system. Okay. If you can build an approximate solution of the Navier-Stokes system, so by this I mean a solution of this system with a force term here that is small in some sense, then if you can do that, the next question is, can you justify Prandtl's ansatz? Okay. Okay, so that's for the, say, favorable scenario. And so what are the properties of the solution? And then what do they mean about the system?
You say properties of the solution of Prandtl.
Mm-hmm.
You say properties of the solution you mean Prandtl.
Of Prandtl, yes. Yeah. Here, yeah, of the solution of Prandtl. And so, for instance, if the Prandtl solution develops singularities, what do they mean? So here, it's at the level of the Navier-Stokes system. Maybe, and this will be what I will be talking about, maybe in some cases they are irrelevant, meaning that they are an artifact of the Prandtl system, and they mean that the Prandtl system is a bad approximation, actually, when the system develops a singularity. But they don't provide any insight on what the solution behaves like at the Navier-Stokes level. They just mean that locally, in the vicinity of that singularity, the Prandtl system should be forgotten about. Okay? So that's what I meant when I was saying that mathematical analysis can be used as a toolbox. Okay? It indicates where and when the approximation is expected to be valid. Okay? If it's not, then the next step is to try and modify the system to provide some to provide some nice answers. So can you modify or adapt the Prandtl system to get positive answers? Okay. So actually, in what I will prove, there are a lot of negative results. Okay, there are some positive results, and there are some cases in which we can provide some positive answers and go have yes, 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 yes. Okay, go all the way to here. But this is okay. There are these cases are well identified, and I think that outside of those, unfortunately, the idea is that the Prandtl system is not very good. Okay, so I don't know if that's unfortunate for this audience, because it essentially what it means when you have either a singularity or when you have ill-posedness, this means essentially that you're creating an instability. Maybe it just means that there are some small scales within the system that you need to take into account. Okay, and in particular, you have small tangential scales that you completely forgot about when you designed the Prandtl system. So, you know, this is why I thought that this would be relevant to this audience, because it's a kind of it's a way of, say, describing the transition towards turbulence. Okay, this is essentially for a completely laminar model, even though there are small scales in the normal variable. But then if you create singularities or if you create instabilities, then this means that you need to take into account these small tangential scales. Oui.
In the impulse case, what happens if you go to further order in the Prandtl on that?
Yeah, this I intend to talk about it tomorrow. So typically, so it will be in this scenario. Okay, the idea. So I can give you a small preview. Say. The idea is that in a number of cases, the Prandtl system has a bad behavior either because you create a singularity or because you have an instability. This means that you have some small tangential scales in all the cases that I know of. And these small tangential scales mean that when you discarded here the viscous term in the tangential variable, this was a mistake. You should have kept it. Okay, maybe you assume that it was negligible, and in fact it's not. And so the hope is that when you put it back into the system, you have some kind of regularizing effect in the tangential scale, and maybe this will smooth out your singularity or smooth out the instability that you have. Okay. And so maybe if you're looking at some higher orders in the coupling, so you couple the outer flow with the boundary layer flow at a high order in order to take into account this regularizing effect of the viscosity, maybe we'd have a system that has some nicer properties. It's not so clear. Okay? Yes?
Are you talking about two-dimensional flows?
Yes, I am.
Only?
Yeah, only. Yeah, 2D.
And where is the limit epsilon goes to 0 there?
Yeah, can you justify Prandtl sentence, this is what it means. It means if you look at a solution of the Navier-Stokes equation, so you cook up an approximate solution based on Euler plus Prandtl, essentially, and you prove that the difference between U epsilon and this approximate solution is small. Okay, I don't have enough room to write all of this down, but that's the idea. Okay, yes?
So I have a question about the question, can you build an approximate solution for S?
Yes.
So you mean the answer is no is when we found them to this second line, or how does it be?
Well, okay, so what happens quite often not just for this boundary layer or fluid mechanics system, but in a general way, when you say you have singular perturbation operators and small scales and so on, in order to have a nice approximate solution, you actually need to build a solution at a very high order, much more than the main order term. Okay, you need to build many, many, many correctors in order to have a nice approximate solution. And so the question is this: can you do that? Can you go to a high enough order that you have that you satisfy the equation with a small remainder? Other questions? Okay, so yeah, this is everything that I will try to talk about, and so I will start with the stationary setting. So this was for the preliminaries, and now I will look at the stationary problem. Oh, and one thing that I didn't say is that, so here I talked about well-posedness in a very broad sense. This question doesn't make sense in a full generality, okay? So the answer will very much depend on the setting that you're looking at. So by setting, I mean many different things. I can mean the properties of the underlying flow, okay? Is it monotone? Is it convex? Is it a shear flow? Things like that. Or I'm talking also about the functional analysis setting. Okay, so maybe this is more interesting to the mathematical part of the audience, but depending on whether, so to put things in a very broad terms, it means do you authorize yourself to look at an infinite number of derivatives? Okay, are you okay with looking at solutions that, say, live in the analytic world and have infinitely many derivatives? Or do you want to work with solutions that only have a finite number of derivatives that are essentially controlled by your energy? Okay, when you want to stay, and the answer will be very different depending on the point of view that you adopt. Okay, so I will. So this is more concerned with the, say, time-dependent setting, so I hope I will be able to cover it in the third lecture. But yeah, so the question doesn't really make sense in full generality. You need to restrict it to some kind of context. So now I'm looking at the stationary problem. So the stationary Prandtl equation is the same as the one that is written over there, except that you discard the time derivative. Minus dYy up equals minus pressure gradient. You have the divergence-free boundary condition. And up equals Vp equals 0 at y equals 0. And limit as y goes to infinity of up of xy is some u infinity, which is prescribed. Okay, and now I also need to put some boundary conditions in X. So let me explain this. When you look at this equation, let's say that you forget about this bad transport term for a moment. Okay, so let's say that you're just looking at u dxu minus dYyu. Okay, this looks a lot like. I hope I can convince you about that. It looks a lot like a diffusive equation. So if you look at dxu minus 1 over u dYyu equals something, this has a kind of, it's a bit like a nonlinear heat equation, or diffusive equation, at least when u is positive. Okay? So when u is positive, it looks a lot like a heat type equation, and so you expect the equation to be well posed when you go from x equals 0, say, to some x positive, okay? And so in that case, you will enforce some boundary data for x equals 0, so some inflow boundary data, okay? And then if u takes positive and negative values, then it's more complicated because you have some in some cases it's a forward parabolic equation, in some cases it's a backward parabolic equation. In some regions it's one or the other. Okay, so let me explain this. So this is the typical picture that you might have if you look at a cross section of the flow. If your velocity profile looks like this, so this is u and this is y, okay? If your velocity profile looks like this, meaning that it's positive everywhere, so here u is positive, and so you really have a forward parabolic equation. Okay, and in that case, you will enforce some inflow boundary condition at x equals 0. So u at x equals 0 is some u naught, and you solve for x positive. Okay, so this is the first case that I will be looking at, and today I will only be looking at this case. Okay, and then there is another situation. No, of course, then you can complicate it a lot, but let me say the first level of complication is this one. You can also look at cross sections of the flow that look like this. So this is still y, and so here in this region u is negative, and here in this region, so this is u is positive. Okay, so here you have a reverse flow close to the boundary. Okay, so you actually have some vorticity, right? You have the velocity is going like this. So in this case, it means that you have a backward parabolic equation close to the boundary and a forward parabolic equation far from the boundary. So in that case, it's more complicated. Okay, so you have a backward parabolic flow close to y equals 0, and forward one far from it, y equals 0. Yes, sorry, it's UP. Thank you. It's UP. Okay. Okay, so this situation is more complicated, and in that case, I won't even try to solve it globally. So I will look at what happens, say, in a section with between finite x0 and x1, and that's it. Okay. But these are the main two cases that I will be looking at in the stationary problem. Okay, so for the stationary problem, here's a small outline of what I'm going to talk about. So first, I want to show you some well-posedness results in the case where u is positive. Okay, so these results go back to Oleinik in the 60s, but okay, I'll present a small proof that I think actually has not been written as such, even though it's somewhat present in the literature, but it will allow me to introduce some tools that I can use afterwards. I will talk a bit about boundary layer separation. and the so-called Goldstein singularity. And then I will talk about the last part. So see here, the first item is the yes answer to the well-posedness in the case where U is positive. The second bullet point will be this item, the formation of singularities. Okay. And I will also talk about this last part, the justification of the ansatz. So this was my purpose for today's lecture, but maybe I will overflow a little bit on tomorrow's. And then okay, I will mention some open problems on. So since this, I will show that generically well, not generically, but at least in some cases, the solution may develop some singularities, which means that maybe the model is not so good in that point, and you should modify it. And so, say I will present some adaptations or modifications of the system. But so for this, it will be mostly open problems because I think there are essentially no works on the stationary case that actually allow you to smooth out the singularity, or non-mathematical ones actually. And actually, I don't even fully understand what is written in the fluid mechanics books to present such systems. So maybe this will be actually some kind of discussion with the audience if people have a better understanding than I do. To me, it's still very puzzling. And then eventually, I will talk about problems with recirculation. But this will be for tomorrow. Okay, so this is all the things that I would like to cover in the stationary case. So I will start with the well-posedness in the case where U remains positive. Of Prandtl. I start with Prandtl. I really follow this decision tree. So I start with the well-posedness of Prandtl. Once I have a nice solution of Prandtl at hand, then I can consider the convergence of the justification of the Prandtl ansatz. But first, the very first step is to look at the Prandtl system and to check whether or not the equation is well-posed. Okay, so it's well-posedness without recirculation. So in the case where U is positive. So again, this was done by Oleinik in the 60s. So what Oleinik did was to perform some change of variables in the equation in this one, okay? So it's U. So she relied on a nonlinear change of variables. And this change of variables is valid only when U remains positive, so when it keeps a constant sign. And thanks to this change of variables, she was able to transform the stationary Prandtl system into an actual local nonlinear parabolic equation, which looks a bit like the porous medium equation. And then you have a whole range of parabolic techniques to prove well-posedness of the equation. So, but the proof that I'm going to present today, actually it's a sketch of proof because, as I said, I don't think it's written like that anywhere. I'm fairly confident that it works out, but okay, I'll give you some ideas and you can try it as an exercise. but maybe it's close to what is written in a paper by Samir Ayer and Nader Masmoudi in 2022. There are many variants of what I'm going to talk about. And the way that I'm going to write it, it's also in a paper that I wrote with Nader Masmoudi on the Goldstein separation, even if that was not our purpose was not to prove well-posedness. So let me show you how it works. So since UP-VP is divergence-free, you can introduce. So the first step is to somehow modify the system in order to exhibit actually this parabolic behavior, okay, to really highlight it. So you introduce the stream function. Say psi p. I'm going to drop the p's at some point, okay, because I think I'll just forget about them at somehow. And so I can write up as dy psi p. Okay, so maybe it's minus the stream function, but and this vp is dx psi p. And then when you look at the transport term, this up dx up plus vp dy up. This you can write it as up dx dy psi p. And here this vp will be minus dx psi p dy up. And here you can recognize a derivative. So this is dy of dx up psi p over up multiplied by up squared. Right? Everyone agrees? Okay, so now you can rewrite the equation as, so dy of dx psi p divided by up minus 1 over up to the square dyy, and I'll keep things grouped for a reason that will become transparent. Here, the right-hand side, I'm just going to denote it by f of x. So f of x is minus dp e over dx. It's the right-hand side, okay? Equals 0. Okay. You integrated this with respect to y, and you multiply by up. Dyy minus f of x equals 0. And then I differentiate it again once with respect to y. It is 0, but I would like to keep it because I want to avoid any singularities on the boundary. The thing is that you see when you take the trace of the equation on the boundary, you have, so the first two terms are 0 because u and v are 0. And so it means that dyyup is non-zero on the boundary and coincides with the right-hand side. And because I'm dividing by u square, which is 0 on the boundary, I'd rather keep something that is, yes, actually, okay, it's a misprint. This dyy, the parenthesis is not correct. That's the issue. It's like this. And okay, I forgot to correct it in the other one, but okay, and so then the last operation is to differentiate this with respect to y, and then you get an equation for up. Okay, so you obtain dx up, and you have a complicated operator, which I'm going to denote by m of up, applied to dyyup minus f of x. This is equal to 0. And this m of u, the operator m of u, when I apply it to a function h, it's dy times u integral from 0 to u of h over u square, like that. Right? Everyone agrees? Okay, so maybe you don't find it, so you find it a bit weird. Maybe just let me write it mu in a different way. You see, when I differentiate this is h over u, okay, when the derivative hits the integral, plus some lower order term. So this is lower order, at least in terms of h, okay? So here you see that now all the nonlinearity and the non-locality is hidden in this operator mu. And somehow you see at main order, the equation that you have is really the one that I wrote over there, this dxu minus 1 over u dyyu, okay? So the main order operator is this one, and it's really the one that I announced, okay? So obviously you still have some non-locality. I didn't do any real change of variables here. I just did some kind of manipulation on the equation. But yeah, that's the idea. And the thing is that you can prove some dissipation properties for this operator mu. And so you have a small lemma. So, which is some, say, coercivity property for the operator mu, or rather, in this case, for some operator which I will denote by lu, which is dyy composed with lu. Okay. You can see that if I apply two derivatives to the equation, okay, I can do that, then I will get an equation for dyyu, which will involve this operator right there, okay? So, in fact, it's more convenient to work with this one. And so, if you assume that u is a smooth function, so I think I need u to have three derivatives. So h3 log of 0 plus infinity. And you assume that u is positive everywhere, that u on the wall, so for y positive, okay, obviously. U on the wall is 0, and dyu on the wall is positive. So this is the same assumption as the one that Oleinik had. And you take h to be a smooth function, say c1 of 0 infinity, such that h and its first derivative vanish on the wall. And then you can look at, so I think, the integral from 0 to infinity of lu of h times h over u. And you will do some integrations by parts. And this will be greater than some constant times the integral from 0 to infinity of this quantity plus, so I think it's u square divided by u fourth of h square. So this is a nice positive term, okay, which will actually give you some diffusion. And then you have, and here the constant small c is explicit. It's like 1/2 or 1/4, something like that. And then here you have some constant depending on u, and you have a lower order term. I think, let me just check the exponent. I'm not sure if it's u or u square or u. Maybe it's just u. Yeah, it's just u. Okay. I'm a bit short on time, so I won't prove the lemma, but it's very, very easy. It's, you take the expression of LU and you perform integrations by parts, and that's it. I mean, it's not very complicated. The important thing is really that this operator exhibits a diffusion-like behavior. It's coercive. Okay. And so this should allow you to prove well-posedness. So again, it's not written like that in the literature, so I'll mention it as an exercise, but I'm very confident that it works. It means that it's bounded from below by something that is strictly positive. It's bounded from this quantity allows you to control a norm on H, up to some small lower order remainder. That's the idea. Okay, if you didn't have this term here, you see that this dissipative operator would allow you to control this norm. Okay, let's say, imagine that you can compare this with, say, if you look at the classical diffusion-like operator. If you look at this, for instance, then you integrate once by parts, and this is equal to this quantity. Okay? So here, it's a variant of that computation, taking into account the fact that U has some variation, so we have additional terms when you integrate by parts, you have some non-local terms that you need to take care of, and so on and so forth. Okay? But that's really the idea that you have in mind. You want to somehow compare LU to something that has a diffusion-like structure. Okay? And so this lemma is telling you that LU really behaves like something like two derivatives and a division by U. That's the idea. Yes?
How do you define the well-posedness?
So yeah, I'll write a theorem, but let me write the theorem by Oleinik, and hopefully that will answer your question. So this one is by Oleinik. So you take an inflow boundary data, which is U not P, which is a smooth function, so C2 and bounded on the whole line. Okay, which is, so there are two important, maybe it's a little more, okay, I'll put C3 because I cannot remember exactly the exponent and it's irrelevant to what I want to say. So you take an initial data, there are two important conditions, or yeah, maybe three. So it needs to be positive for Y positive. So you are in this scenario. It's 0 on the wall. 0. And its derivative is is positive on the wall. This is the crucial assumption. And you also need to have some compatibility conditions, which I'm not writing down. Okay, and then for any such initial data, the stationary Prandtl equation has a unique solution. C2 and bounded solution on some interval zero x star. Okay, so you can construct a solution locally up to some abscissa x star that you don't know a priori. The only thing that you do know is that if your pressure gradient is favorable, meaning that minus dPe over dx, this is positive, right? Okay, the right-hand side here is positive, then x star is equal to plus infinity. So you can construct the solution globally. Okay, the idea is the following. So as long as you have a positive derivative on the wall, you can prove local well-posedness. Okay, and here, if you enforce a right-hand side that is non-negative, then you will preserve that property. In fact, you will actually maybe it will be better and better. The derivative will be bigger and bigger and remain positive. And so you will always be able to construct something locally. That's the idea. But as we will see, on the other hand, if this is strictly negative, then generically you will create some singularities. And so the solution will only live on a short interval. Does that answer the question? Yep. Okay. So that's the theorem by Oleinik, and so the sketch of proof that I'm proposing, but I leave it as an exercise, and as I said, I don't think it has been written like that. Set sketch of proof. So at least for the short time existence, okay? The first step is you construct a reference solution, or a reference profile, say, which I'm going to denote by uref, which is smooth. So this one is at least C3. So it should coincide for x equals 0 with the inflow data. It should remain positive on the wall. And of course be 0 on the wall otherwise. Okay, so it should satisfy all the assumptions of the lemma. And I think you need something else. So it's almost you also need that the third derivative on the wall is always 0. Okay. So you construct this reference profile, and then the idea is to construct a solution in the vicinity of that reference profile. Oh yes, and one assumption that I forgot about is that it should cancel out the f of x, okay, on the boundary. So you construct this reference profile, and then you construct a solution in the vicinity of uref by an iterative scheme. Okay, so you define a sequence un, which is uref plus some corrector wn. Okay, and un plus 1. So say that W0 equals 0, and Wn plus 1 satisfies something like dx un plus 1 minus m un dyy, maybe I put W here. n plus 1 equals some remainder that you can compute in terms of uref and so on. Okay, so the idea is really to build upon that structure to construct a solution. Yes.
What's the motivation for this peculiar third derivative condition?
This one, it's because okay. I remember that I needed it in the. I think it's just a compatibility condition. It's actually it's always satisfied by the equation when you differentiate the equation and you take the trace. You find that the solution necessarily satisfies this. And I think it allows you to have a nice structure. So you see, when I wrote down this lemma, h here will be the second order derivative. And so in order to perform all the integrations by parts, I will need to have a vanishing third order derivative on the boundary. So it's always satisfied by the equation. But so I construct solutions that satisfy this property. And so I ensure that my reference profile already satisfies it. That's the idea. Okay, so once you have identified the structure, you just build the solution in this way. And so then you prove convergence of the scheme. Okay. Okay, so I haven't checked out all the details, but I'm fairly certain that it works. So I leave it to you. But I don't think that you really need to do any kind of change of unknowns. I think this works out well. Okay, so until I don't know, you know. In any case, I'll finish later on. So when you want me to stop? Yeah. Yeah, perfect. I can adjust in any case. Okay, so then you see the solution that you construct in general only has a finite interval of existence. Okay, so you might wonder why is that and what happens in the vicinity of this the maximal say abscissa of existence. And so this was investigated first by Goldstein and Stewardson in the 50s and 60s. So the idea is now to look at the situation. I don't know if I wrote down some kind of, yeah, so it's well-posedness. So now it will be the singularity formation. So you look at the situation where you have an adverse pressure gradient. Meaning that the f of x that you're looking at is -1. So let's say that you have an inflow boundary data that looks like this. So this is again UP naught. Then the thing is that because you have an adverse pressure gradient, your source term is somehow pushing the solution in this direction, okay? So its influence will be to decrease the value of the solution. But if you start from a monotonic data, you preserve the monotony, okay? So at later times, what you'll have is a profile that looks the same way, but just steeper. So it will look like that, okay? So this will be at a time x, which is smaller than x star, until you reach a point and you see that this is really, when you look at Oleinik's theorem, the important assumption is that the vertical derivative on the wall should be positive, okay? So in other words, at the moment where the Oleinik solution ceases to exist is the moment when this solution is violated, and then the profile will look like that. Okay, so at x equals x star, almost a consequence of Oleinik's theorem is that dy up on the boundary vanishes. Okay, And if at least conceptually you keep pushing the solution in that way, for abscissas smaller, bigger than x star, you will create a reverse flow on the boundary, and so you will be in the situation that is over there. Okay? So now the idea that what I want to talk about is what happens in the vicinity of x star, which is defined in this implicit way. So x star is defined as the point where the vertical derivative on the boundary vanishes. Again, okay? So again, this was investigated by Goldstein and Stewardson in the 60s. It's two different papers, okay, which are actually almost 10 years apart. So I think Goldstein is 1958, something like that, and Stewardson, I'm not so sure, but about 10 years later. And so their idea was to compute an expansion for a good candidate for an approximate solution using some clever self-similar variables. I think one of the issues of the construction is that not all terms of, so it was built as a series, as a formal asymptotic expansion. I think not all terms of the series could be completely identified, but in any case, what they found was that dy up of x at y equals 0, this should behave like x star minus x to the 1/2. And so this is called Goldstein singularity. Okay, and around the same period, but with completely different assumptions and methods, Landau proved the same rate. Okay, and then so there were not that many mathematical studies for a while. There was one result that was announced by in a paper by Wine and E. Or he announced a joint result with Caffarelli, I think in 2000. But I think they never published the complete proof of the result. And then with Nader Masmoudi, we gave a proof of that result. And there are also some related results by Yang and Wang. So let me just, I'm not sure of the date. Yeah, by Shen, Wang, and Zhang. But they don't prove exactly the same thing, actually. Maybe I'll come back on that. I won't have time tomorrow, today, but maybe I'll talk about it tomorrow.
So X star is where the flow separates from the wall.
Yes, that's the idea. So in this case, it's defined as the solution where Oleinik, the abscissa where Oleinik solution ceases to exist. I'll come back on that tomorrow, but the idea is that because you have this behavior, the VP becomes infinite at x star, which means that there is a very large amount of normal velocity that exits the boundary layer and enters the interior flow, which is another description of separation, and actually it was Landau's description. Landau's description was rather to say that Vp at x equals x star should become infinite, at least for some points. Okay, which means that the velocity exits the boundary layer, which is another way of formulating the separation. Okay, and so here is the idea, and I'll finish tomorrow. So the observation, it relies on the following observation, that the stationary Prandtl equation with a source term f equals -1 has a scaling invariance. in the following sense. So if UP is a solution, and you compute U lambda, which is lambda to the -2 UP of lambda to the 4th x lambda capital Y, this is still a solution. SP for any positive lambda. Okay? And actually, I think Goldstein's and Stewart-son's expansion more or less relied also on this scaling invariance. And so the idea is to perform some kind of a change of scaling, a dynamical change of scaling. In the equation in SP in order to zoom in, to zoom on the separation point. And when I say dynamical here, it means that I'm not going to take an arbitrary sequence lambda that converges towards 0. I'm going to take some lambda that actually depends on x and that depends on the solution itself. Okay, so here is what I'm going to do. So you take lambda, which is actually some lambda of x, and this is really important, which is precisely the value of dyup on the wall. Okay? So this is expected to go to 0 when you go near x star. Okay? And then you define some capital U of S and Xi. Those are my rescale variables that I will define in a moment. Where you have, capital U, this is this lambda here. So capital U of S and Xi. This is lambda to the of x to the -2. U of S and lambda Xi. I'm not sure. Yes, this is it. So Xi is capital Y divided by lambda. Okay, and ds over dx. So this is my rescaled tangential variable is lambda to the 4th. Okay, and then I look at the equation for capital U. And here, the equation for capital U looks like this. It will be UUS plus V U Xi. So this is the same as Prandtl, okay? Minus d Xi Xi, U equal -1. Okay, so this is exactly the same as Prandtl. And then, I should have left more space. So again, this is just Prandtl. So here I just wrote down the scaling invariance. Okay, when you do the computations, you find that you have a scaling invariance. But you have an additional term here, which is B. I'm not completely sure about the coefficients, so I'll just, I'll take my notes. There's a 1/2 and a, minus U squared plus 3/2. Plus 3/2 U Xi integral of U. I haven't defined V or B yet. Okay, the B is missing. Okay. So this is the equation that I will be working on tomorrow in the beginning. So you have dsu plus d psi v equals 0. So indeed, v is the integral of v. And b here is minus 2 lambda s divided by lambda. And so it's minus lambda x, lambda 3, if I'm not mistaken. Minus 2 lambda x, lambda 3. So here is the important thing. If you, if you just had, again, if I had taken b, lambda to be constant, there would be no b. See, the b would be 0. And I just would have written down the scaling invariance. Because my lambda has variations, there is an additional term here, which is this modulation term. Okay? B is as much an unknown as u, obviously. Okay? B depends on it depends on lambda, so it depends on the solution. Right? So the idea is to try to find a nice behavior for B, to find the behavior of B, and and to do that, we use techniques of modulation of variables. Which were introduced, I think, by Zakharov and also by Sulem and Sulem in order to study some singularity formation in dispersive equations. So here, the equation is not dispersive, but I think what is important is not really the dispersive part, it's really the fact that the equation has a scaling invariance. This is really the crucial thing. And this scaling invariance allows you to rewrite a rescaled equation. And the purpose is really to find a regime in which this modulation term is of the same order as the other ones. Okay, so everything plays at the same scale somehow. And so the scheme of proof, so the strategy, say, is as follows. So there is a step 1 where you completely forget that B is a parameter that depends on the solution. You treat B as an independent parameter. B as an independent parameter. And for any small b, you try to build an approximate solution. Solution of the type, so U will be some main order profile, which is a kind of ground state, U0, plus some correctors that are, so you have some kind of asymptotic expansion in powers of B. Then, ouais, une minute, je finis. Then you try to identify a kind of least action principle. Least action principle that will give you a law for B. Okay, and that will, so you kind of, you try to select among all these possible, you have a whole family of potential approximate solution, and you need to pick one that should be the most stable one. And this most stable one will dictate what the law for B is. Okay, so again, it's the selection of the best approximate possible solution that gives you the law for B. Okay, and then you prove the stability of this approximate solution. And proving the stability of this approximate solution will also allow you to prove that the law for B is the good one. And then so that's step 3. And the last step is to to go back to the original variables to check that you actually, to check what that means for the original variables. So I will do this tomorrow, and I'll stop here.
Thank you.